the presentation. Just a few housekeeping. If you have any questions, just please post it through the chat box bottom of the screen. So if you have any questions to answer, to ask verbally, then just switch on your microphone. The speakers will try to address it. Okay. Okay. Let me introduce briefly the two speakers. We have the first one, IR Ko Chai Huat. Mr. Ko was last time our MWA council member. Mr. Ko, hi, Mr. Ko.
Hi.
Okay.
Nice meeting you again.
Okay. So Mr. Ko's fields of special competence is specialized in water supply, dam, hydropower, flood mitigation, and coastal engineering. Currently, he's involved in the Upper Padas hydropower project, Tawau Dam project, Papa Dam feasibility study, and several dam safety reviews. He's holding a master degree in civil engineering and also have a membership with the ACM and MWA. Okay, next speaker, I introduce IR Stephen To Chin Kok. Okay, Mr. To is the Dam Department Section Head. Sorry, Mr. Ko just now is the Managing Director of Angkasa Consulting Services, and Mr. Ko is the Dam Department Section Head under Geotechnical and Dam. He's a Geotechnical and Dam Engineer, also under Angkasa Consulting Services. Field of special competence is his experience in dam engineering, geotechnical engineering, and hydraulic structures involving investigation, design, dam safety assessment, and rehabilitation of existing dams, emergency preparedness. Also overseas experiences in structural and geotechnical engineering in Russia, Indonesia, Trinidad, and Tobago. He's also holding a Bachelor of Civil Engineering honors. Yeah? Okay. I think without much ado, I will hand over the presentation to IR Ko to start the first presentation. Please welcome Mr. Ko.
Okay, thank you. Thank you. Is the screen already? Share screen?
Yes, you can see you.
Can see me, yeah?
Yeah, you have to share your presentation.
Okay, can see my screen?
Yes, good.
All right. Okay, thank you very much, and good morning to everyone. In today's in my talk, I will give an overall view of the various types of dam commonly built in Malaysia, especially for water supply purposes. And towards the end, I will talk more about the technical issue or design issue concerning specifically to the concrete face rockfill dam. Okay, so the content of this talk this morning, first, introduction to the dam and reservoir. Number two, the needs and functions of dams and reservoir. And three, the types of dams. Four, salient features of dams. And fifth, design issue for concrete face rockfill dam. So, introduction. Special natures of dams. Dams are often built from a combination of natural and engineered material. I think this is an important concept. It's a combination of natural and engineered material. Usually store large volume of water and are very dependent on the foundation and abutment for support. The reservoir usually inundate large area. The impact on the environment is very significant. So all dams have unique characteristics that usually include site geology, construction material, and structural form. Dam is subjected to impact of natural hazard, especially earthquake, extreme flood event, and landslide. So all these are natural hazards that actually will lead to have an impact on the safety, long-term safety of the dam. So all dams have to design to be able to withstand the expected loading condition from the natural hazard. Dams store large volume of water and possess large potential energy. Because of the height of the dam and also large volume of water, the destructive force of the water store is very great. and the consequence of dam failure is catastrophic. That's why the safety of the dam is paramount, very important. The variations in geology, the building materials, geometry, means that it is not practical to develop a standard code type design or standard analysis or evaluation procedure for all type of dam. It is just not quite possible to have a code-like type of design guideline, because every dam have their own unique features. Geology of the site difference, the environmental conditions difference. So each dam have to be designed to suit the actual condition at the site. Each dam is unique and must be treated individually, taking all relevant factors into the account. Okay, next one, I will briefly talk about the needs and functions of the dams and reservoir. The type of dams, the functions of the dam can be outlined in this slide here. Top in the list is a water supply, at least in Malaysia, water supply, irrigation, hydropower, waste storage. This is more of the tailing dam for those mining. Flood mitigation or flood control, sediment control, sediment and water quality control. This number 6 is more related to check dams for the control of sedimentation in the reservoir. And number 7 is recreation. Say for example, Putrajaya Lake is a recreation, but in Putrajaya there are actually 3 dams in there. You may be able only to see 1 dams, but actually there are 3 dams in there. Okay, there are also dams that is used for secondary usage, more for aquaculture. Now, recent years, with the increase in the solar energy development, there are quite a number of reservoirs, especially in Korea and Japan, that actually build floating solar on the reservoir. So these are the secondary usage of dams. Okay, recreational dams, Putrajaya dams is a very beautiful lake built with 3 dams that I have mentioned, and it is the first time that in Putrajaya, we are the consultant actually for the design of the lake. The labyrinth spillway, as you can see on the left-hand corner there, the first labyrinth spillway is built in Malaysia, and it's actually quite a unique feature there. At night, especially with the light shining on, the water spilling like a small mini waterfall. Okay, this is the Kinta check dams. This is the one that is actually, they are altogether 3 check dams there, more for to retain the sediment due to the massive landslide at the Post-Lim Highway that brought a lot of millions tons of sediment into the river, which if not done retained by the check dams, it will all end up in the Kinta Reservoir. Okay, the safety of the dam, the impact of the dam on the environment is quite tremendous, very significant. So the question of dam safety is a predominant requisite pervading all dams project, which is I have said before. And the society attach great importance to the environment and social aspect of the dam and reservoir, and expect them to be addressed seriously. All dam projects should meet the 3 basic criteria, basically technical first, including the environmental and social, economic and financial feasibility. And today, dam projects have to satisfy the 4th criteria, which is social and political acceptance. So the decisive factor for such acceptance is dam safety and the compatibility with the environment. So dam safety is still paramount. Dam projects should seek to achieve a balance across competing objectives of environmental preservation and protection, and to provide the highest level of operational integrity and safety that can reasonably be achieved. Therefore, it is necessary to find a solution by striking a balance between the competing objective of environmental conservation versus the need of dam project for many benefits for socio-economic development of the society. So we can see that dam project now become very controversial, especially in the developed country. Building dam is a very big issue. There's a lot of resistance because of the impact on the environment, especially the loss of the flora and fauna. So, but in Malaysia, we are at a stage that we need to build some dams. If we don't build, I think a lot of states will have faced the water supply problem. So we have to strike a balance between the preservation of environment and also the need for this the services. Okay, the useful life of the dam is also governed by the sustainability of its reservoir. So catchment management plan and reservoir sedimentation management plan are necessary for the dam and reservoir. So a lot of them actually suffer from severe sedimentation, and I think this is quite well-known case that in the case of the Ringlet, the Sultan Abu Bakar Dam in Cameron Island is very seriously silted up because of the catchment erosion. So TNB have to spend every year millions of ringgit to mitigate this sedimentation problem. Okay, the types of dam. First is the high in the list is the earth-fill dam. In Malaysia, most of the early dams is built from with the earth-fill. So I just briefly outline the key features of this type of dam. Stephen, can you see the pointer? Can see a pointer? Okay. The concept is that in this Malaysia context, because we are in the tropical country, and with the very heavy rainfall, with the wet weather and also heat, the depth of weathering of our rock formation is quite deep. So in most of the dam site, the depth of weathering can range from 10 to 40 meters, which is quite common. So with such a deep weathering depth, other type of dam, especially the concrete gravity dams and rock-fill dams, become expensive. If you have to strip away all the overburden to reach the sound foundation level, the rock level, then the volume of the height of the dam, instead of 50 meters, if you should strip 20 meters, becomes 70 meters. And what you strip, you have to fill back with the embankment material. So the volume becomes very large. But however, under this kind of condition of deep weathering, it means that earth-fill material is quite commonly readily available near to the dam site. So the cost of the earth-fill material is relatively cheaper compared with rock-fill or concrete. In fact, it's only 1/10 of the cost of the concrete dam, the material itself. So earth-fill dam become competitive because of this reason, that the dam, because of the very broad base, with a gentle upstream slope and downstream slope, the stress on the foundation actually is quite small. So we do not need to strip away the overburden layer. So most of the dam is just found on the overburden. So long as it has sufficient bearing capacity and the long-term settlement is not excessive, it is acceptable. So the earth-fill dam, the key feature is that you look at the central core, the center area, this number 1, this is zone 1. This is the key feature of the earth-fill dam, is the clay core. This is the impervious material, the barrier. And it's a form of water barrier. So at the foundation, if it is the foundation is pervious and the seepage rate is too high, normally a concrete cut-off wall or bentonite concrete wall is normally constructed. Like in the case of Mengpang Dam, we have actually provided a plastic concrete cut-off wall at the foundation in order to limit to cut off the seepage. And at the rock formation, we install this cement grout curtain so that all the fractured areas in the rock formation can be sealed. This is not only just to, this is necessary so that we can have a continuous seepage cut-off barrier formed by the clay core, the concrete cut-off wall, and also the grout curtain. More for safety reason, because if we do not have this seepage cut off, and the seepage from the reservoir will penetrate to the foundation, and we might exit to the toe of the dam, it will cause uplift and also internal erosion and piping. So this type of dam, normally for safety reason, we have to provide a chimney filter. This is actually very vital zone, the zone 2A material. This is a filter. This chimney filter actually serves two functions. Number one is to intercept the seepage that is passing through the clay core, so that any soil particle will be retained by the filter, and the water will be discharged. The seepage water will be discharged. And together with the chimney filter, we have a horizontal drainage blanket. This is actually to carry the seepage water safely out of the dam. So we have also provided, in the case of Mongkwang Dam, this is a 55-meter high earthfill dam. In the case of Mongkwang Dam, we have also provided the intermediate filter blanket, so that to dissipate the pore pressure during the construction stage, because we are placing material at slightly wetter, about 2 to 4% wetter than the optimum. So there is a risk that the pore pressure build-up might cause stability to the dam. So this is the function of the filter blanket. Now for the upstream zone, normally the upstream zone is provided more with a gentle slope, more to take care of the rapid drawdown. Because if you have a drawdown of the reservoir level, rapid drawdown can cause the stability problem to the upstream slope. So that's why you need a more gentle slope. So for long-term protection of the surface is normally provided with a riprap. And the downstream, we have to protect against the scouring action of the rain. So normally turf soil and turfing is provided. But in the course of the Mongkwang Dam, we have actually incorporated the rock toe. This is quite an important feature, because the rock toe here add on as a counterweight against the potential uplift due to the seepage. And also it safely strengthen the toe. The weakest area of the earthfill dam is always at the toe area, the downstream toe. So this needs to be strengthened. So the detailing actually is very, very important. The problem of piping in terms of safety record, earthfill dams suffer two major problems. Number one is the overtopping damage by flood is quite high in terms of the history of the dam. So overtopping by damage due to overtopping by flood is ranked number one in terms of the incident and failure of earthfill dam. Second incident, the highest, is the internal erosion, the piping. This internal erosion, because earthfill material itself actually is quite weak. So the seepage water coming in and with a high pressure is actually under certain condition because during the time of construction, the material may not be well compacted. Sometimes some area, especially near to the concrete surface area, compaction is poor, and then foundation is not even, or sometimes the more porous material are being used. So this is all quality control problem. So you may have already defect in the sense, inherent defect in the material itself. So under the high water pressure, actually the water from the reservoir under high pressure can actually penetrate through the embankment, and then it actually causes fracturing of the soil itself, because of it crack open, basically progressively crack open the soil, and so that it lead to concentrated leak that form. So this the leak is propagated from the upstream reservoir side continuously to the downstream side. So if the leak is not sealed and the erosion, internal erosion continues from upstream to downstream, it gradually, eventually form a small conduit, and the conduit will carry all the soil material out of the dam. So eventually, a continuous pipe will form and become a piping failure. That's why the term piping failure came in. It's called pipe, basically. So these are the two main common problems that is the potential failure mode for the earthfill dam. So when we deal with earthfill dam, this is the two weakest problem. Okay. Now this is the example of the Mengkuang Dam. This is the dam that is earthfill 3 kilometers long, 55 meters high. It's it's the longest water supply, longest dam, I think, water supply dam in Malaysia. 3 kilometers altogether. It's formed a very beautiful lake there. Oh. Concrete gravity dam. Okay, the next type of dam that I want to briefly introduce is the concrete gravity dam. Now, in concrete gravity dams, the technology using roller compacted concrete is quite common now, which is especially for high dam. Concrete gravity dam is actually quite competitive. The dam itself, because it's constructed out of concrete, is very secure. So the requisite is that in order for this type of dam to be competitive, like in the case of the Sungai Kintar Dam, during the feasibility study stage, we have actually evaluated 4 types of dams. Finally, the competition between the concrete face rockfill dam versus the RCC dam become these two options become more competitive. Because the dam, the height of the dam itself is 90 meters. So under very high dam, for the case of Sungai Kintar, the site condition is that the geology is that is from granite. So you can get the good quarry material for the concrete aggregate. The two requisites must be there. Number one is that you got to have a good, strong enough foundation in order to found the concrete gravity dam. Number two is that for the cost of construction is very much governed by whether you can develop a quarry near to the dam site or not, so that the haulage of the material can become cheaper. So for the case of Kintar, we have the quarry which is very nearby, less than about a kilometer away. And fly ash, because this type of dam, for RCC dam, we need fly ash. For every cubic meter of the RCC, we need 90 kg of fly ash and also about 90 kg of OPC, the cement. So the fly ash actually is derived from obtained from the Manjung power plants. And cement is also from the cement plant. So the cement plant nearby. So it makes this RCC dam a lot more competitive. So some feature of this dam is that, typical feature is that this dam, typically the upstream face is vertical, and and towards the bottom is slightly inclined, and this is more to enhance the stability against sliding. And on the downstream side, normally it's steeper than 1:1. In the case of Kintar, it's 1 vertical to 0.7 horizontal, so it's very steep. So on the dam itself is actually incorporated a spillway, it's an auger crest spillway, and then also with the step chute. Actually, step chute is a form of to dissipate the energy of the spilling water. So the water that is overspilled will lose the energy. Some of the energy will be killed. And then finally, at the toe here, there's a roller bucket to further reduce the eroding energy of the overspilling water. So this type of spillway is quite commonly built in the RCC dam. So from what you can see here is that because the dam body is built from concrete, therefore you can actually build the spillway on the dam body itself. So there's no need to build a side spillway as in rock-filled dams or earth-filled dam. You need to have a spillway to be built at the side of the abutment, commonly cut involving high cut slope, and can be very costly. So for the case where you have a very steep valley, to build a side spillway is just very, very expensive. So it is this type of dam become competitive. RCC dam become competitive. And another feature is that because for the purpose of a diversion, you need not build a diversion tunnel. In the case of Sungai Kinta, we need a box culvert. 2 box culvert is enough for the diversion purposes, because the risk of overtopping and damage is the extent of damage in the event of overtopping by flood during construction stage is limited. It's not extensive. So the diversion become quite cheap, cheap way. And also because of the RCC dam and the upstream phase, we do not need to build a separate draw-off tower. So the draw-off, the intake for reservoir intake can be attached to the upstream phase. So it makes the draw-off tower very, very cheap. It's a very cheap way of building it. So with all these saving in cost of the separate spillway, saving cost of the diversion tunnel, saving the cost of the draw-off tower, all together make this RCC dam competitive. Although the concrete itself is expensive, it's very expensive. So typically it's about 100 to 130 ringgit per cubic meter at least. That is a cost that we estimated at that time. So it's more than 10 times the cost of the earth-filled dam, but you're saving in other costs. So this type of dam the way that it's constructed is mixing the RCC in a very dry condition so that it can be compacted with the roller, like the compacting soil using the flat drum roller. And that is the terminology, roller compacted concrete come from, RCC come from. So in this type of dam, actually is all constructed in layer by layer. Each leaf is 300 mm thick. So that become a weak feature of this type of dam is because of the many leaf involved. Like say for example, the height of the dam is 90 meters. You almost have 300 layer or leaf. So these are the point where the seepage water can leak through. It's one of the leakage potential seepage or leakage path. So in the dam itself, we have to have some drainage gallery so that the drain, whatever seepage passing through the transverse joint, it can be collected and safely passed through to the drainage and discharge downstream. So this is broadly the features of this style dam. This is a view of the Sultan Azanzar RCC dam, which is Sungai Kinta. This is the Uruzalai dam, the RCC. This is by, I think this is consultant is SMAC. This is TNB dam for hydropower. Sungai Kinta is by Angkasa, by us, but this is by SMAC. So you can see from this aerial view that at the center, the Augie crest is here. And the downstream, this is a spillway chute that I mentioned. So in the case of Uruzalai, instead of a roller bucket, they have this stirring basin as a form of energy dissipator. And the downstream slope is all in the form of step, Okay, certain features of dam and reservoir. Example, rock-filled dam, earth-filled dam. This is Mengkuang Dam. Just to outline what has been done in the case of Mengkuang Dam. Because Mengkuang in the they are involving raising the existing dam, and which is green color, and also building the completely new dam on the adjacent valley. So the old dam is raised by 11 meters. So at the bottom section, it shows to you how the raising of the dam is being done. Finally, that is adopted. The top one, it was the original design. But later on during construction stage, early stage of the construction, we had made a revision to the design. And so that the construction is made a lot safer, because in the original design, there is a need to build a concrete cutoff wall at the downstream toe as a form to continue the cutoff. So the safety to the existing dam become an issue. So we have finally decided, and with the agreement concurrent of the client, of the owner of the project, we make a division. So this is as a result is a lot safer to build. This is just a section through the draw of tower. Okay, a bit of the construction, how this is being done. You can see that the top here, this is actually the concrete slab for the grouting. This is for the curtain grout and also the conservation grout. This is a picture showing the construction machine, the clamshell used for the construction of a plastic cutoff wall. This is a very heavy machine, and the machine can penetrate the overburden to a depth of about 40 meters. So it grabs the material and then form a continuous trench, and they fill up with the bentonite and cement. Conservation grouting work continue from the concrete pad. Jet grout, there's a jet grout construction, jet grout wall construction at the spillway areas. This is just a picture showing the chimney filter on the right hand side, the placing of the filter blanket or horizontal drainage blanket. The picture shown on the left hand side. Same picture, you can see the chimney filter is raising up, and then side by side is the placing of the clay core material and also the downstream slope material. This is a completed view, overview of the reservoir. It's a beautiful lake after it's completed. Just a picture showing during the construction stage of the draft tower, a completed draft tower. Draft tunnel. Construction of the lining, reinforced lining for the draft tunnel. The completed lining of the draft tunnel. This is just a picture showing the construction of the valve house connecting to the draft tunnel. Okay, that is for the Earthfield Dam. Now I just quickly show some example of the RCC dam construction, the Sultan Azam Dam or the Sungai Kinta Dam. You can see from this view that earlier on, you can see that this is downstream side is in the form of step. This is on the downstream view. Oh, sorry. And on the left hand top corner, you can see the flip bucket is down here, and the chute wall is here. You see the chute wall, and this is on the downstream side. Sorry, on the bottom picture, you see the vertical face of the RCC dam, and at the center here you can see the reservoir draw-off structure. As I mentioned before, that it just is attached to the upstream face of the RCC dam, so make it quite very cheap to build. This site actually show a more close-up look of the roller bucket here, and after the step spillway. Oh. And on the left side, you can see the gallery, the drainage gallery. This is actually just it's a box cover, like it's basically a square box covered built inside the RCC dam body, where all the drainage vertical drain are built, and also the instrumentation, a lot of instrumentation are also built inside along this gallery. This is the picture showing the pressing of the RCC dam itself during the construction stage. The RCC mixing plant. More picture about the construction stage of the dam. Oh, sorry, going backward. Okay, you can see here that this is the surface of the RCC dam. It's very, very flat in each layer. And the cleaning of the surface after each lift. This is if the next layer that you place is exceeding certain time, then that layer basically have to be clean cut, and whatever loose particle have to be cleaned off. And sometimes a layer of mortar, cement mortar, is pressed so that the new layer can be adhered properly to the old layer. The top here, you can see the spreading of the RCC material, and the compaction of the RCC with the 6 passes with a 10-ton roller. And on the left corner, the bottom corner here, this picture shows that the construction of the transverse joint. This is actually to allow that it's a preset contraction and expansion joint, so that it minimizes the crack in the RCC. This is a construction of the RCC and grout enriched RCC, essentially near to the outer surface, in order to increase the durability of the concrete. We need to add in more cement grout, so that the RCC, after adding the grout, is become more durable and stronger at the surface. At least the upstream portion, about 400 mm surface is grout enriched RCC. The bottom picture here, you can see the installation of this copper water stop at all the joint. Some of the instruments, like the strain gauge and also the pressure cells, are installed in the RCC. Okay, this is a completed pictures of the RCC dam. Okay, the next topic that I'm going to talk would be the Rockfield Dam. Okay, this is a section, the cross section of the concrete face Rockfield Dam. Actually, this section design is taken from the current project, the Sungai Tawau Dam project. Okay, the key feature of this Rockfield Dam is that basically it is constructed of rockfield. The main embankment is all rockfield material. So in a layman term, this is a very big pile of rocks. And the rock itself is stable. And from the natural angle of repose, the rock field that is designed is more gentle than the natural angle of repose. so as to enhance and make sure there is a stability is not an issue. Although we say that it is a pile of rock, but it's a lot of design issue principle have to be exercised, because for successful construction of the rockfill dam, the selection of the rockfill material, the grading, the zoning, the concept of zoning and all this, it become very, very critical. As I will mention later on, there are quite a number of rockfill dams actually have very serious deformation problem and the cracking in the face slab, which lead to major leakage problem and also safety reason. So basically, the dam is built from the rockfill material, and then on the upstream side, this is concrete face rockfill dam. The upstream side at the top normally is constructed, a wave wall is provided. And on the upstream face, this is the face slab. So the face slab is a concrete slab, basically generally about 250 mm to a meter in most of the dam, but in the lower dam, maybe it's 300 mm. I think in thickness of the face slab is quite common. So the dam itself consists of the concrete slab on the upstream face, which form the water barrier. And at the toe here, on the upstream toe, there is a slab, a concrete slab. This is called the print. We call it print. Actually, the print is very, very critical. The print is a component that actually connect the face slab to join it to the foundation, secure the whole dam face slab to the foundation. So the print have to be sit. If it is a rockfill kind of foundation, then the print must be seated on, must be found on groutable rock. So normally, if the site geology is favorable, we will take it down to almost fresh rock, slightly weathered to fresh rocks, so that we can just construct the grout curtain and the conservation grouting. So it will make this part very secure. So in terms of dam, you can see that the rock fill itself is very stable. But the bigness of this dam is that the hydraulic gradient at the print here is very, very great. So because this site is subject to water level, this is a water level. Say if you have a dam 60 meter high, like in the case of Tawau Dam, the water depth is about close to 60 meter. And the print itself is only about 8 meter long. And downstream of the concrete slab, this area, this is all rockfill material. And rockfill is porous. So you can see that the hydraulic gradient is very, 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 very high, very, very large. So the integrity of the foundation just beneath the print is very, very critical. If this is not well constructed, the leakage through the dam is very, very high. And especially if the foundation is founded on erodible material like overburden, then the failure through the piping is very high risk around these areas. So in order to overcome this problem, I will talk about it. There are ways to secure this, is to extend the print further downstream, extend the print. And in some cases, the downstream side, a layer of sockclick are provided. Sockclick with BRC, and then on top of the sockclick, they put a layer of the filter material. So that in the event that there is any erosion, the erodible material subject to the seepage, carried by the seepage, this will be intercepted by the filter zone. This is actually practiced also in the case of Bakun. I will show you a picture later on how this is in the case of Bakun, how they designed incorporating the soft plate layer and the filter. So this is also the same principle also adopted in the Tawau Dam. So another feature that I like to talk is that this zone 2B, this is actually a cost filter. This zone is particularly important. And this zone 2B, it has to be, the material have to be selected in such a way that it give a uniform support to the concrete slab, so that the concrete slab will be even. All the stress evenly, the stress due to the water load is evenly spread out, so that we do not have any concentration of pressure at any particular location. So beside providing a uniform support, this slab, this zone, the 2B zone, is also very critical in reducing the seepage rate through the slab, because the leakage through the joint in the concrete slab is quite common. Quite common. It's just a matter of extent how high the seepage rate. So in the event of any crack develop in the concrete slab, or especially leakage through the joint, this zone 2B actually play the role to reduce the seepage rate. This is a concept that is actually evolved after several dams incident. They changed the specification of this material to make this zone become semi-pervious. Previously, in those dams that is designed before 60, especially 60, this layer immediately below the concrete slab, they screen away all the sand-sized particles and the silt. They remove all those smaller particles. It's actually more to ensure that this is a free draining. But later on, they found out that the big problem encountered is that when they remove the sand material portion, the rockfill material become too coarse, and then it also lead to segregation. So when the seepage occur, the dam couldn't behave as what is designed intended. So the selection of the 2B material had gone through quite a long period of evolution. This is important. Now this zone that is color blue, this 2C zone actually is acting as a transition between the 2B and the 2A. Basically, it's acting as a filter for the 2B material. So this is a zone 2B. Basically, this is a fine rockfill material. And then the zone 3A, this is the one, the brown color. This zone is the one that actually takes most of the water load. So all the water load, pressure acting on the face slab is transferred into the rockfill at the upstream side. And it will all transfer finally to the foundation. And because of this zone, the modulus of this material is very important. So that it has to be very well compacted. The material must be well graded, so that compaction can be effective. So this zone is rockfill zone is also important. So the zone 3B is less critical in the sense that it don't really directly subject to the water load. So the thickness of the fill layer and the material selection can be a bit more relaxed. Another feature that I like to talk about is that to enhance on the upstream toe, in order to enhance or to lengthen the seepage path, actually we normally will incorporate the earth fill zone on the upstream face, and then also random fill material. These are earth fill material pressed on the upstream side, so that to reduce to lengthen the seepage path, so that we can reduce also the hydraulic gradient. So basically, this is the key features of the dam, of the rockfill, concrete face rockfill dam. Good example of the CFRD dam is the Bakun Dam. You can see from this picture that is all the vertical joints are indicated there, shown there. The Bakun upstream side, the reservoir, beautiful lake created, and you can see the vertical wall here is a vertical wave wall. Downstream slope of the Bakun Dam, very nicely constructed the rockfill surface with the ramp going up to the crest. Okay, the next topic that I want to talk briefly is the design issue for the concrete face rockfill dam. In this topic, I will cover basically this subtopic. First is the general arrangement and the reason for selecting this type of dam. The number two is the rockfill zones, the zoning and their properties. The concrete face, foundation treatment, and then some of the case history of the observed settlement and displacement of the face slab and joints, and some example of the observed leakage of CFRD, and finally the failure path for the CFRD. A bit of the history of the CFRD. Basically, the design of CFRD dam is even up to now can say that it's mainly empirical, and is predominantly based on experience and precedent, and also judgment. To a certain extent, is also judgment. Experience and that judgment actually very, very important. Historically, the first rockfill dam with a concrete face was constructed in California in 1895. And there are several early dams, CFRD dam actually leaked quite excessively, mainly due to the deformation of the concrete face, the face slab deformed, and resulting in opening of the joint and the cracking. This is a big problem for CFRD. Now, the early dams up to the late 1960s, they were mostly constructed with dump rock and without compaction. So as a result, the modulus, the compressive compression modulus of the dump rock fill is actually low. The detailing also is not up to the required standard. So these two weaknesses lead to the compression of the central part of the dam and resulted in the increased opening of the joints, including the opening of the parametric joint. These are the common problem, leakage of the earlier dam. So up to the 60s, the concept of building CFRD have actually taken a change because of the several incidents. And they finally realized that all this dumping of rock without compaction is wrong. So dam have to be, the rock fill have to be compacted in layer. And also the dumping had another problem, is a segregation problem. So that once it's segregated, you have a lot of large particles in one area. So you have a lead to the large void in the rockfill zone itself. So the segregation lead to migration of fine from the adjacent area. As a result, it's very deformation of the rockfill embankment become quite a serious problem. So later on, they changed this of dumping to compaction, using compaction. That largely advocated by Terzaghi. And in the history of CFRD, there's one personality, this Barry Cook. This is a very well-known. He's actually can you say a father of CFRD. He's very he have done a lot of deep consultation to many countries in the worldwide in the CFRD one. And he's the one that actually come up with a lot of detailing for CFRD that finally get a lot adopted by this ICO. ICO actually adopted a lot of his idea. There are two personalities in this Rockfield Dam. One of them is Barry Cook. Another person that is also quite well known. And ICO's later on I will mention about the ICO's some of the guidelines on this selection of the material. The zoning principle I have already covered. Basically, the principle of zoning is that the selection of the material is actually from finer rockfield material gradually increase the size as you grow upstream. So during the pressing, actually you are pushing the coarse particle towards the downstream toe. So you have a gradual transition of material from fine to coarse downstream. So it gives you a very good hydraulic the flow pattern from fine to coarse. So there's no the material, if it is well selected there no deformation. Number one is that the rockfield zone itself must not deform. Second thing is that the rockfield material itself must be free draining, so that there's no pore pressure built out. So if it's free draining, there will be no pressure built out. So this whole embankment will be dry, so that there is no water pressure involved. So this embankment will be stable. As a result, this will be very, very secure. And rockfield dam, one thing good about rockfield dam is that it is very good in absorbing energy of the earthquake. So in those country or those area that is prone to earthquake damage, concrete face rockfield become quite a good design option. Actually, there was a dam in China that the Xipingfu is a quite well-known case that the epicenter is actually only 19 kilometers away from the dam, and the dam at the crest is shaking at 1.2 meter per second square. But the damage is mainly at the crest and the upper part of the slab. So this rockfield dam actually is quite good in the earthquake areas. Okay, the zoning is, I leave the slide here, but I'm not going to go through. I've already tell you more the general concept. So I cannot be reading through all these things. Okay, a bit of the transition material, which are the coarse filter, basically. In the terminology for earth field, this zone 2B is called a coarse filter. But when you apply to the CFRD or rock field, this is called the transition. This transition I have mentioned before, it evolved through many dam incidents that finally they adopted that through this table, you can see that this Sharat is one of those pioneers also in CFRD, working quite a lot of jointly with the Barry Cook. He's an expert in filter. He's actually my guru also. I actually like his paper because his research on filter also I have also great interest in the design of filter, and have published some paper on this. So in 1985, Sharat has actually advocated that for the zone 2B, they should limit the maximum size to 75 mm. And he has also strongly advocated that in order to minimize the extent of segregation, he advocated that at least 40% of the rockfield material should be finer than 4.76 mm. This is a sand size. So if you have 40% of the sand size, you will minimize the risk of segregation. And at the same time, in order for the zone 2B to be semi-pervious, we need some percentage of the fine. So he advocated that we should have about 2 to 12% of the fine, so that this the overall grading is a very well graded, and this well graded material itself must be internally stable. That is to say that it must not be get graded. That means that you do not have some missing particle size and lead to gap, a certain gap that the fine material can migrate into the bigger particle. So that is internally unstable if it is graded. So what he found out is that from the research, he found out that if you include sufficient percentage of the fine, especially the 75 micron particle, you can actually get a very good semi-pervious material, because we are trying to achieve a permeability K 10 to the power minus 6 meter per second, so that in the event of any leakage or crack through the slab, it can actually control the seepage or leakage to the CFRD. But later on, what they found out is that this percentage of fine have to be reduced. So because what happened is that if you have very too high percent of the silt, especially the fine silt, you actually increase the risk that the rock fill itself, after it compacted, it can crack. So there are quite some incidents that during the construction, they noticed that there are deep crack developed into the rock fill. So there is a fear that if the thing crack, that zone 2B zone crack, then you have the seepage, then the seepage will go through the crack, and then it will lead to unstable condition in the rock fill. So back in 2010, ICO, International Committee on Large Dam, they advocate that limit the 75 micron portion to 7%. So that actually greatly reduced the risk of sustaining a crack. Yeah. So this is the one that I really adhere to. I like my zone 2B to follow ICO guideline. This is safer. Okay, basically I have mentioned about this, so no need to go through. This is an example of the grading, the 2B grading. This is the grading that was adopted by ICO in 1989. It's more to illustrate the get graded this line. So there are some particle around 1 mm to 7 mm size is missing here. So this is no good. We want a smooth, well graded, so that internally this must be stable. Okay, general requirement for the rock fill, we have first, the rock fill itself must be free draining. That means they will be to avoid the build up with the pore pressure during construction. And they must also allow the control of the drainage water, which might leak through the face slab. And at the same time, the rock fill should have a high enough modulus so that they do not deform easily, and so that the face slab do not deflect. So to limit the face slab deflection to an acceptable level. Also, the long-term creep deformation of the rock fill should be small enough to avoid excessive long-term settlement. But most importantly, the material itself must be readily available as a quarry run product, and without having to process it because of the economy. So it's important that this material, once it's developed from the quarry, the extent of processing can be limited. Okay, layer thickness. This is there's a guideline that for the zone 3A, generally the layer thickness shouldn't go beyond 1 meter. And the zone 3B, they allow 1.5 to 2 meters. Again, again, this is very much dependent on the quality of material. For Hydro Commission of Tasmania, HEC Tasmania, they actually advocate their guidelines that when you the zone 3B for lower quality material, they want it to limit to 300 mm to maximum of 600 mm, so that they can minimize, they can ensure that the compaction, better compaction, and also this is actually minimize the risk of deformation. So different agency and owner, they have different guidelines. But generally, for the, it is all agreed that the zone 3B condition can be more relaxed, because it's, as I said before, it is not the taking the water load, but it's just as a support to the zone 3A. Now in 1987, they want to achieve a well-graded rock fill, and also to ensure that the rock fill is quite free draining. They come up with this guideline that 20%, not more than 20% of finer upon 4.76 for the rock fill, 3A and 3B, and then not more than 10% of finer than 0.075 mm, so that they want the material to be really free draining. Okay, a bit on the print. I have mentioned about the print before. First, let me show you the type of prints. Okay, there are various types of print, from a horizontal, conventional horizontal print, to the inclined print on the abutment. And in the case of the weathered ground condition, we have the internal extended slab that is constructed downstream of the parametric joint from the connecting from the horizontal print. So this is actually very important for those situations where the print is founded on weathered rock. Like in the case of tower, this whole foundation, we are building the dam on pyroclastic rock. Is a volcanic rock areas. So the material itself is quite varied, and there's the quality of the rock can vary a lot. So to ensure that the print is seepage is gradient is small enough, we have actually incorporated the internal slab on the downstream side wherever necessary. And then in some cases where the whole rock fill and the print is founded on overburden, then you need to incorporate a concrete cut-off wall or diaphragm wall. In the case of tower, we have actually incorporated 3 rows of wedge stick mixing jet grout wall. This is a deep foundation cut-off. It can extend to about 30 meters deep into the so that it can found into the rock formation, which is in some area is about 30 meters below. So this is very important because of without this, if you found the slab, the whole spleen on overburden, because of this foundation, the overburden material is actually very erodible. And then under very high seepage gradient, the material, once it's eroded, the piping will develop. So the construction of the concrete wall, this WSM jet grout wall, is very, very critical. And on the downstream side, we have also provided a layer of this socket. Okay, just a bit of concept on this. How this ICO has actually in 2010 is adopted from British Shara 1989. He has actually come up with a guideline for the design of to determine the width of the slab of the print. So this is depending on the type of foundation. This ranging from non-erodible, which is rock, basically fresh rock and good rock, to slightly erodible, which can be, say, moderately weathered to material, and erodible material, and highly erodible material. Like in the case of the right abutment of the Tawau Dam, on the overburden, this material is classified as highly erodible. So the maximum hydraulic gradient or the print width with respect to the water depth, this column C, for the case of Tawau, it must be in the 1 to 3. The rest of the parameters is rockfill quality designation, weathering degree, ranging from 1 to 5, from fresh to completely weathered. And then this is the F, actually is the consistency degree. That means the consistency of the rock for rock quality. For very hard rock, very good quality rock is 1, and very friable rock is designated as 6. And G is the weathering discontinuity. So one thing you notice that this is to classify this non-erodible to slightly erodible without actual parameters is quite difficult sometimes. So it's between erodible and highly erodible. To be able to distinguish it more precisely, my personal view is that this classification can be made more scientific and more definite. Perhaps with the parameters like soil erosion constant, things like that. So there's a lot of research can be done in this aspect to be able to quantify and classify the material more scientifically, rather than to have a so-called a kind of subjective description. Okay, a bit of this. Some print detail, I think, is getting a bit into too much detail, but you can take your own time to read if you really are into this concrete face rockfill dam. Parametric joint, I think, yeah, this is another area that is actually very, very important. The parametric joint that I've seen, just I show you, because of the historically, a lot of displacement occur at this joint because the stress is when the face slab deform, it pull away from this joint. So when the displacement is too large, leakage will go through here. So the protection of the joint is actually very, very important. There's a lot of detailing around this joint, this parametric joint, incorporating water stop, several types of water stop, copper water stop, hyperon water stop, and then also with the mastic materials. Earlier on, they use this mastic, some use of fly ash. I think recently there are also some example using silt and fine sand, so that it is in the event of any leak, all this material can be sucked into the leak, and then it's sealed. Hopefully it can jam inside here, inside the leak, at the joint here, so that the leak can be plugged and can be sealed. I think that's the concept. Okay, this is just some of the historical record of some of the dams that the displacement of the joint, especially at the parametric joint. Now, foundation treatment is another topic that is itself is a big topic. So I probably will not have the time to go through it. But I think I just want to carry the message in this talk now that the rock fill material, the selection is actually very critical. You make sure that there's a sufficient strength in the rock fill, and the rock fill itself must be well compacted. It must be well graded, and then it must be free draining, and the modulus is high enough so that it don't deform. So if you have fulfilled all these conditions, then the face slab will not have to deflect so much. If the face slab don't deflect, then the joint, the vertical joint, horizontal joint that is in the slab itself will not open up. So it will not pull away from the parametric joint, so that leakage will not happen. So this is all important to protect the face slab from opening up at the joint. But the foundation treatment is to ensure that whatever erodible condition of the foundation, it must be treated, well treated. Okay, this is a bit on the testing of the material, because some of the material, the rock fill, can disintegrate. This is actually quite a common problem. So in order to check whether the material will disintegrate or not on the long term, they have actually performed this soak and wet cycle test using some are using ethylene glycol to check to test whether this integration is serious or not. Now there's an example I'd like to show you is the Bakun. Bakun, as you know, is a concrete face rock fill dam, and the site there's a gravity. Basically, the rock fill material, it consists of 60% of gravity and 40% of mudstone. And they know that this material, there's a concern that this material will disintegrate on the long term. So the very extensive tests were performed to prove the extent of disintegration. So at first they do some tests without confining, unconfined. After compaction, they didn't confine it, and then they performed the cycle of soaking and wetting, and then they subject to compression test. Compression, they found that the extent of disintegration is very, very high. So then subsequently, they further test, different type of tests were incorporated in order to. So finally, they found a test that can do this test, and they found that about 10% of the volume of the rock fill have this disintegration problem. This is actually the foundation treatment. I'd like to talk a bit on the grouting. On the grouting. Okay. This is the Bakun design, as I mentioned earlier on, that in the case of Bakun, because it's a sedimentary, this gravity and mudstone, and there is this upstream area, some areas actually is on weathered rock. So a layer of sockling was incorporated. So this is a good feature in order to ensure that the whatever seepage that may pass through this thin print foundation can be safely, the seepage can be more spread out. Yeah. And also they have incorporated the filter, pressure layer filter on top of this socket. Okay, I'd like to mention a bit on the construction of the print. Very often you find that the foundation for the print, because of the irregular surface of the rock after excavation, we have to resort to the use of the dental concrete and sometimes concrete block. So they found out in some of the dam, the concrete block, once it's exceeding 3 meters, the stability of the block itself is a big question. So there's a lot of investigation and research into how to design the block so that the stability can be ensured. Okay, a bit of the general behavior of the rock fill material. You can see from this picture, at the end of the construction, the face slab, the shape is actually bulging out. This is a deflection down, and then this is bulging up. So this is a general the dashed line indicate the deflected shape of the body. So this at the end of construction, and then another after the reservoir filling, then due to the water pressure, the face settlement pattern changed to this shape. So you can see that during the impoundment, because during the impoundment, your face slab, everything is already constructed. So if there is a deflection of the face slab, then it definitely will lead to shear and tearing at the parametric joint. Then leakage will be a big problem. Okay, this is just some indication of the showing the movement and direction of the stress zone. You can see from here that this is tension, then center here is a compression. So the direction of movement near to the parametric joint, you can see from here is pulling away. And you look at this bottom figure here, the movement can be opening up the joint in this manner, or it can rise and settlement in this manner. So this parametric zone is the one that actually will have to take a lot of the stress at this area. So any deformation of the slab ultimately will affect this parametric zone. So this is an important area. Some of the measurements are done on several dams on the crash sediment. So crash sediment is also quite common. I think you can expect up to 1%, quite common. Most of the dam 1% of crash sediment. Some of the cases of some of the dams suffer from cracking of the face slab, like at the bottom here. You can see the picture here. This in the case of Campos Novos. This is in Brazil. This dam. This face slab cracked mainly because of is built on quite a steep abutment. So there's a high stress concentration in some area that lead to the cracking. Leakage record. You can see that the leak from this record, you can see that the leak some of the dam actually suffer more than the leak is quite high, like the case of Otto Anchicaya. The maximum leakage rate recorded is about 1,800 liters per second. This is very, very high leakage. So anything more than 1,000 liters per second, this is classified as a leak. Okay, this is my last topic. I quickly go through this one. This is the failure assessment, failure path for the concrete face slab. You can see from this picture at the bottom here. Finally, at this is the weakest area. It can fail. Is I have mentioned that it might be opening of the parametric joint, or cracking of the vertical joint, or cracking of the face slab, and internal erosion at the print foundation and piping of the print foundation. All eventually center around this area. As a result, the foundation get the erodible material get eroded, and the erodible material all carry into the rock fill, and the hole become bigger and bigger, and eventually the whole thing just flow, and this become a collapse eventually. So this is the postulated by Farrell in his book, Professor Farrell in his book. He has actually tried to come up with a method to assess the failure mechanism, and also the assess the probability of failure. But these are all historical, based on historical data, especially piping is a very complex phenomenon. It's not very easy to assess the probability of failure. Very, very complicated. So I think with that, I thank you so much for your attention. And then I shall pass to my colleague, Stephen To, to continue with his talk. So I have just, my timing is quite good. I take 1.5 hours.
Yeah.
So okay, thank
That's
you very
nice.
much for your patience.
Okay, thank you, Mr. Koh. So I look at the chat box. There's no questions for now. So I think we proceed with Mr. Stephen To present his presentation. Welcome, Mr. To. Thank you.
Thank you.
How do I do that? How do I answer? Done already.
Yeah, already done.
Okay, I will share my screen now. Okay, thank you for this opportunity to present this talk. Along with Engineer
sorry.
Paul. He have given a very good insight of all the designs issues and what is the design principle behind the whole design of all these dams. So the first thing on the topic.
Sorry, Mr. Stephen. Kita ada suara background bergema.
Okay.
I think because of the two
I think from Mr. Koh, I think.
You can just close the volume of your computer. Hold on. Okay. All right, we are good to go. Okay, first of all, we have actually discussed about the overall principle, and in this particular talk, we actually talk more towards the design principles and issues on CFRD. And so we know about the principles, we know about the designs, and how about for the constructions. So more often than not, we actually find that in order to carry out whatever as per design, the dam design towards the construction, there are some of the particular construction features that is incorporated into it so that we can actually construct as per design. So I'm here now actually to show some construction features of CFRDs, which is actually commonly used to resolve some construction issues and make sure that the dam is constructed as per design. To begin with the construction of the dam, we always have these river diversions. And the reason for all these river diversion is we build the dams, we always build it in the dry conditions, whether it's a raw fill dam, earth fill dams, or even RCC dam or concrete gravity dams. All these are built in the dry conditions. And when we look at the river diversion, is the first thing to be done. For the case of CFRD, we always have some options because of the rock fill condition that is actually able to take overtopping during the constructions. We can find two methods of river diversion in CFRD's design. We can always do with the conventional way, where you can build a diversion tunnels, divert the river water, and build the construction with the upstream cover dam and downstream cover dam and create this dry area for the construction of the dams. And for the case of CFRD, the concrete face rock fill dam, you can actually incorporate another method, which is actually allow for overtopping on the rock fill with certain protection measures during the course of the constructions. So this is well already been practiced in many CFRDs. So for example, so you can see that most of these CFRD that use this method, they will incorporate some steel reinforcement at the downstream face of the rock fill to prevent the failure of the rock fill during the flowing, overtopping. And you can also use the gabion method as well by anchoring it into the rock fill as well. So let's see what are the things that is incorporated. These are some examples of many of those early days. We'll say early days means these are the dams built during the 1970s, during the time where CFRD has just emerged as one of the good options to build dams. They are very versatile and they are actually very easy to be built. And we can see that all these sample case study, most of them are from Brazil. And it was at that time, there's a lot of, Brazil is actually one of the countries that actually try to go for these CFRD's design in the early days. So if you look at this, how they actually do their diversions, you can see that over here, there is always a part they call priority sections. And this is actually looking towards downstream. The river diversion is actually still on, they don't obstruct the river. They build some of the priority sections, whether it's on the left bank or right banks. And if you look at this, there's also towards the upstream and downstream directions, they always can also build this priority sections and followed by the actual one. So what do we mean by priority sections? These are actually what they have opt for if they don't use the diversion tunnel method. Means during the construction of the rock fill, they actually allow certain degree of overtopping through their rock fill. And the priority section is only built when they are ready to go higher, when the construction is ready to go taller, and they actually have already done most of their grouting works and their foundation works. So these are the examples of how it's being done. And in this case, you can see even the left and right bank were to be constructed first while leaving the center part open before the actual diversion is carried out through the overtopping method. So these are some examples of what we have done, even in our own design. These are some of the examples of our design which we actually try to consider using this priority section method. And these are one of the working files that we actually do. We actually have to type with the construction schedule and how this can be done in the shortest time possible. And that is actually the benefits of using rock fill. So if you look at this, we have to time our construction at the left and right abutment where the river section is in the middle in this case. And then after that, we have to plan for the priority sections for the diversion. So all these are actually can be done because of the nature of the rock fill in itself. They can drain a certain flow through their rock fill. And if we look at the design of the CFRDs, these are actually one of the important chapters if we were to do a design of seepages through rock fill. So these are examples, some past examples that we have on our projects in Malaysia. These are some examples that further illustrate how it would look like before diversions. So we can see that the left and right bank of the rock fill is constructed while leaving the center portion. And when it's a drier season, this is where the construction of the river section will proceed quickly and go up to become the priority sections. Some further example, this is Macadino dams, and this is TSQ1 in China, which they use the gabion method to reinforce the rock field during the overtopping through it. So these are some of the method, some of the good features that you can see for a rock field dam, and in this case, especially for CFRDs. And these are the pictures showing the rock field overtopping of the Tianshanqiao Dam, Tianshanqiao 1 Dam in China. Most likely most of the time this rock field overtopping is also designed up to a 500 years return period kind of flood. So this is actually the limit that is set for the typical construction of a CFRD at the shortest time possible schedule. The next item, before we, I think the earlier slides by Engineer Core, they put a lot of emphasis on how we can construct the CFRD, the rock field embankment, in the case of ensuring no segregations, and how to ensure the whole embankment is constructed in such a way. But how about those at the edges of the embankment, whether it's downstream edge or the upstream edge? So in this case, particularly for this CFRD, the upstream edge is of very important importance. They cannot fail. They cannot actually have segregations. They cannot actually have a loss of material during the rainfalls. They should be protection against any erosion, because we know that the one that is the founding plane of this face slab is actually seated on the zone 2B, and this contains some fines that can be eroded as well. So protection against it is required. And because this is a rock field dam, the upstream edge more often than not is in the order of 1 vertical to 1.3 horizontal kind of gradient. And you can see that this is actually quite steep for human to do some construction. So by having this extruded curb construction, it actually provide a safer construction where humans are not actually working on the upstream edge, where they may be toppling down, because it's not like any other construction where you may have berms all the way every 5 or 10 meters. But for the case of a concrete face rock field dam, it's all the way down from the crest to the toe. So a human construction by the upstream edge is actually not encouraged. And extruded curb, in this case, I will show further, it's actually clean. Once you protect your zone 2B, the zone 2B is protected with this extruded curb, it's actually provide a clean construction as well. So we have talked about how this segregation can be prevented, because when you place the material, this material have the extruded curve of the upstream edge. The compaction of the material can be well done by all those of a typical 10-ton vibratory roller, and it doesn't affect the edge. So the grading of this zone 2B is well protected, well preserved, and they are going to be performing as per design. So another thing is, once this extruded curve is placed, before the construction of the face slab, which is actually the real seepage barrier for the whole CFRD, is also already explained by Engineer Carl, where the stress and deformation of face slab is actually an important issue to be tackled with. So this extruded curve provide a face that is protecting the zone 2B, and at the same time you can actually measure the settlement or deformation along this face prior to construction of the face slab. And usually we adopt in the magnitude of about 7 mm per month. If the deformation of this face before placing the face slab is about 7 mm per month, then it's good to go already, where all this settlement is already within the design tolerance. So extruded curb was first used in the ETA dam, so they are also called as a ETA method as well for these constructions. Next, let's go to some of the how they are constructed. You can see that the plane is constructed first, and then you can see that this area is a very important part of the construction, and usually they are placed with zone 2A, specifically zone 2A, because this is the area where the filter will act as a secondary defense if there is any leakages through the plane area, especially through the perimetric joint. And this curve has also been illustrated in the ICO, and these are actually the constituent material of this curve. The cement content is about 75 kg per meter cube. It's a low cementitious kind of material, and a typical productivity for this kind of extruded curve method is about 2 layers per day. So it's actually good enough for the construction where every day you have 2 layers of this. This curve is actually about 400 mm tall, most of them. That is actually commensurating with your thickness of your zone 2B, which is usually 400 mm per layer thickness. So let's move on. These are some of the examples on the CFRD dam in Malaysia that actually use the extruded curve. You can see this construction of is by the slip form, and they just pour it and they just move on to a certain it's a slip form there, so the construction is actually well controlled. The time is well controlled and compacted along the way. And this is a pictures over here. You can see that this is actually the plane, and then these are actually the extruded curve that is already built on top, which is waiting to a point where the settlement is less than 7 mm per month, and where they will start this when the embankment have reached the crest, almost the crest, just the base of this wave wall. That is where they will put in the slip form for constructing the face slab. So we look at this some of the construction drawing or design drawings. You can see that this is actually the plane, and this is the zone, usually in the order of the first season of those flood. They usually want to construct this area to well compacted to a high modulus, this 5 meter area, and of course this being the lowest point of the plane, which may be irregular and so on. So usually the first season flood area, if the design is to incorporate the seepage through rock fill kind of way, then this area usually will be done in a shotcrete. Then after this area is already well constructed, then only the extruded curve will come in as a typical protection to the upstream face. So these are the interfacing, some of the drawings, construction drawings. We have moved on to the next part after you have your extruded curve. So you ensure that all these rock fill zones are well constructed, and they will function as per design. So the next part is actually talking about when we are going to place the face slab. And we have mentioned just now is 7 mm per month. These are actually quite a typical figures that is being used. If you look at the settlement graph along the upstream face, when they reach about 7 mm per month, that is where the time is quite matured. You can see that there won't be much settlement after that. And this is where even they still do settle maybe for the next month, another 5 mm, 3 mm, or 1 mm. Eventually, these are still within the allowable stress that can actually provide a good base for this face slab. So this is actually a schematic. I mean, how this slip form you can see that the slip form is actually placed at the crest of the construction, and this base is actually usually also the base of the wave wall. And typically for wave wall in CFRD, they are usually tall as 6 meters. That is in order to provide a platform that is wide enough. The crest of this platform usually is in the order of at least 50 meters wide. So we can actually place this whole system in, and these are the slip form that is being placed to construct the face slab as they go up to the top of the crest of the dam. So these are the pictures, how it looks like in the construction, in the actual construction of the CFRD, where this is actually the place where they put up the slip form, all these things, and the concretes and the materials actually will be come in and placed into it. Okay. Okay. These are the few things that we actually have put in to show the two important parts of the constructions of these CFRDs. So there are still many other construction features, but on this talk, we actually just emphasize on the upstream phase, which is the main thing of the CFRD. And many CFRD dam that fails is actually the upstream constructions, as also mentioned by Engineer Cora as well just now. Some of the upstream phase slab cracks and so on. These are actually due to the deformation of the upstream phase of the rock field. So with that, I actually incorporate just these two construction features, and now I actually pass back the floors for the Q&A sessions. Thank you.
Thank you, Mr. Stephen. Thank you, Mr. Kong, for the presentation. Okay, we have about 15 minutes for our Q&A session. So I can see there's no questions from the chat box. Anyone who would like to share your questions and also ask verbally, please do so. Can we have everyone open the video so we can see each other and ask the questions? From the council members, any questions? Ada? The question, Mr. Koh, Mr. Stephen. No questions from the floor this time.
Okay.
Maybe Ruby.
Yeah. Okay. We have Prof. Hanifa here, our Vice President.
On the council, I asked one general.
Okay. Okay.
Since Angkasa, Engineer Kong, you have done a lot of feasibility study. Moving forward for the future, have you identified how many more dams are to build or constructed in this country?
How many more dams to be built in Malaysia?
Yeah.
I think there was from the National Water Resources Study, there is they identifies quite a long list of dam sites they proposed to be investigated. I can't remember the actual figure, but you can foresee that in the area of hydropower, especially in Sabah, Sarawak, I think there's still a lot of potential for hydropower. So currently, quite a number of hydropower projects is being planned. Like in the case of Sabah, the Upper Padas Dam, which we are involved with as the owner engineer, 125-meter high RCC dam for a hydropower project for 180 megawatt hydropower plant project. On the peninsula side, I think most of the hydropower dam, for high dam, I think mostly been built. But currently, Negeri Dam for Kelantan, Sungai Kelantan, I think is under implementation. We foresee that Sabah side, on the Sabah side, there will be more hydropower dam may be built in future. As for water supply, depends on the government policy, because at one stage, it seems like it's going more towards the ORS, offshore river storage, in favor of dams. So I do not have the actual figure as to how many dams will be built. But if you look at the need for water supply, the need to build them for flood mitigation, hydropower, I think there is still a lot of them to be built in the future, in the near future. Yeah.
Okay, thanks.
I can check the statistic from the.
No, so there's still future for the dam, rather than just making good the current dams. Apart from making good the current dams, there's still opportunity for constructing dams. But as you correctly pointed out, it will be more for hydropower than water supply, because now we have this concept of coastal reservoirs and also the ORS. So probably the number of water supply dams might not be that as many as the hydropower dams, I would presume. But since you mentioned that you have done a lot of these feasibility and also the catchment planning studies, I thought you had the numbers. That's why I asked the question.
Yeah. Currently, we are doing the Papa Dam feasibility study. So that is on the Sabah side. Yeah, so it's going to be quite a high dam also, at least exceeding 75 meter high. Most likely, maybe also concrete face rockfill dam. Yeah. And the Tawau dam is under construction now. These are the two CFRD dam that we know we are involved intimately with. And then at the same time with the Upper Paras dam, this is another RCC dam that we are currently involved with.
Okay, just one more curiosity which I like to ask, because you are the best dam engineer in the country. I know when I used to work with City Hall previously, there's always a fear that if something happens to the Klang Gate dams, in case there's a collapse or whatever, KL will be underwater in a couple of minutes. Underwater is not knee deep, it could be a few stories deep of water. Is that a real statement, and is that a real fear today?
Well, the dam was built I think in the 70s. So far from the safety inspections, I think for the case of Klang Gate, our finding, so far we have also involved in a dam safety inspection. There's no real evidence to show that the dam is in any sign of deterioration or danger. Of course, the gate and all this, there are incidents, the gate had to be replaced. Those are movable parts. Other than that, the dam body itself is quite solid. Of course, we also know that there is a fault line that is running along that in that vicinity. We are not sure is on the long term whether the seismic intensity of seismic event will increase or not. So, but this may be even if there is such a concern, the current level of inspection, level of monitoring and surveillance of the dam will be able to dictate whether there's any sign of of defects or whatever that might endanger the safety of the dam. So that is the reason why in Malaysia now we embark on this dam safety management. First is the guideline. The dam safety management guideline, My Dam, is already already implemented. Currently, it's already implemented by quite a number of agencies in terms of safety management. So yeah, but that is a very difficult question, because how do we predict that there is a risk of failure of the Plangate Dam or Batu Dam? And my recommendation, of course, is that the cross monitoring, looking at the surrounding area, not just the dam itself, I think is very critical. Look at the instrumentation, because any dam safety issue will take a long time. There's always a telltale sign that things are not behaving well. You look at the Oroville failure of the Oroville Dam, the Oroville spillway, from their forensic report, the spillway actually detected some sign of defect over a very long span of years. So before it finally failed, it's just that it's very unfortunate that they didn't really foresee that the whole spillway slab can just lift it up like that.
Yeah. Okay.
It's a hard question to say whether there is any immediate question or not on the failure.
Okay, but your recent inspection and all that, you have confirmed that is safe, but still you have to be careful about the future.
Yeah, the close monitoring.
Yeah, close monitoring.
That's the way to go.
Yeah.
There are sufficient guidelines to ensure that the dam is monitored, and to ensure the certain safety standard that can be achieved.
Okay. Anyway, on behalf of MWA, being the chairman of the planning guidelines, I'd like to thank both of you, the authors of the section on the dam engineering, and the talk today. Both the dam engineers are damn good. Thank you very much.
Thank you, Prof. Okay, we have one question from the chat box. Okay, this is from Mr. Thomas Chu. What are the preventive maintenance required for the dams? What is the normal operation problem for the dam? How to discharge the silt built up?
Stephen, you want to take that question?
Okay, I would like to take these questions. So the preventive maintenance required for the dams, actually there are quite many, and they are actually, you can see that in the guidelines, these are actually well spelled out. Not just in these current guidelines, there are also our national guidelines like My Dams, and also some others international guidelines, specifically on the topic of maintenance. And when we look at this preventive maintenance, the requirement is actually, there's one of the issues that always happen to many dam operators is they don't exercise their appurtenant structures. For this case, we are talking about the intake structures for water supply dam case. The valve, in this case, the guard valve and those regulating valve. If we were to look at these guidelines, we actually have to do exercise at least within three months of the last operations. But if you look at generally on the entire scenario of what we can see in many dams in Malaysia, these are one of the main preventive maintenance that is actually lack of for the dams in Malaysia. And what are the normal operation problem for the dam is actually also associated with the maintenance. That is, many dams operators are quite afraid to operate their gates or their valve. So it is all due to the maintenance procedures. And the last question is about how to discharge the silt build-up. In this case, for the water supply dam, we can see that usually many intake structures will incorporate the low-level outlet. So in this low-level outlet, this is where they will be actually operated whenever they have the silt built up near the intake area. But if we were to look at a proper reservoir maintenance, if the dam is designed or the reservoir is being designed in such a way that all these sedimentations calculations are already in order, we rarely find that the silt actually silted up all the way to the intake structures. So, but we also have cases where we have a lot of silt built up due to some constructions of in the catchment. So, and in that case, that is where just now Engineer Core also have shown the check dams can be built to mitigate all these silt build up that can enter to the reservoir. So these are some of the examples that being practiced in Malaysia.
Okay, thank you, Mr. Stephen. Any more from the floor? No more. Okay. I think with that, on behalf of MWA, I'd like to thank IR Paul and also Stephen for the good presentation today. So any last word to wrap up this, or is that all? That's all, huh? Okay, before we leave, I would like to share the upcoming program of MWA. Just hold for a while, yeah.
Dah share? Nampak?
Okay, you dah share, Jo?
Ya, ya.
Okay. Okay, on 29 to 30th November, which is next week, Tuesday and Wednesday, we are having this Water Malaysia 2022 Specialized Conference and Exhibition on Water Quality and Treatment. This will be held at the Pullman Kuala Lumpur Bangsa. It's a physical event, yeah. So we are still open for registration. We hope those who are attending today can register. We still have, places for registration. Okay. You can register at MWA website. There's a link there. All right. Okay, next one, Joe. Okay, this is in conjunction with the Asia Water on the 7th December. We have Regional Water Associations Leadership Forum. We are inviting some water associations head to present, So the registration is also open now. It's a limited seat. We hope you can register soon. It's also available. You can scan the QR code or you can go to the website. Okay. By the way, this is FOC, yeah? Okay, next one. These are the two very immediate events until end of the year. So this is our book that we're talking about today. It's Planning Guidelines and Best Practices Handbook for Water Supply System. Currently, we have volume 2 available for sale. Price for member is 120 ringgit per copy and non-member is 180 per copy. So for volume 1 at the moment is out of stock. Okay, can purchase it online. Okay, the last book. Okay, Joe. Okay, this is Malaysia Water Industry Guide, Statistics on Water and Wastewater. This will we target to publish it by before end of the year. Yeah, this is a collaboration effort between Bekalan Air, CASA, and SPAN, and also the state's water operator. Okay, if you have any inquiries on the events or publications, or you would like to advertise, please contact MWA Secretariat. Okay. So before we leave, let's take a group photo. Joe, please help to take group photo. Okay, everyone, please switch on your camera. Hi, Mr. Lee.
Okay, ready?
Okay. Okay.
You have 2 page only. Ready 1.
Tunggu, tak ada orang keluar lagi ni.
Belum lagi.
Ah,
Ada sikit-sikit lagi. Kita tunggu sikit.
okay.
Okay. 1, 2, 3.
Yeah.
Okay. Then
Next page.
another page. Okay, ready. 1, 2. Ada buka lagi. Okay. 1, 2, 3. Okay.
Okay. Thank you, everyone. Have a good day. Stay safe.